Welcome back, and next up is Sebastian from Trend Micro. Enjoy his talk.
Hello everyone, thank you for attending this presentation. Today I will speak about LoRaPWNing practical radio attacks against LoRaWAN. So I'm Dudek Sebastian, I work for the Trend Micro company, and I've also founded my own company focusing mostly on RF attacks and hardware attacks. So mainly I'm doing that. At Trend Micro we're doing IoT security, and we also help developers in order to secure their own endpoints. So that's why we have also developed our own SDK. And you can also click on the link after the slides will be available in order to have some more information about that. But today, let's focus on the RF attacks first. So you have to know that as an attacker, when doing RF attacks, the MAC layer is one of the most interesting part, because actually in LoRaWAN it allows you, for example, it provides actually a lot of classes, also MAC commands, payloads, and encryption. So this is the most interesting part. So mostly, let's also see the state of the security of LoRaWAN now. So you have to know that here are some relevant publications that were made before this presentation, and they were mostly focused on the encryption side. So mostly, you could see some known attacks that we will be able to do on LoRa. Actually on LoRaWAN, like the eavesdropping, bit flipping, ACK spoofing, LoRa class B attacks, etc. Including also root key management for exposed endpoint, also physical hardware attacks. For example, if you have like an exposed end node that you can find in the wild by, for example, dumping the keys, etc. And the existing tools that were presented before were the following. For example, here's a tool that was presented also last year at the Things Network conference, which was LAF, which is LoRaWAN auditing framework, which is like a great tool to assess LoRaWAN setups, but has some few limitations. And because of this limitation, and also we have also found another tool which is called Chipotle, but because of the limitation of the tools that were made public, we have developed our own tool based on software-defined radio in order to have like more flexibility. And we have also developed our tool in top of this base in order to have like as much flexibility as possible. So let's talk about RF attacks now. So using SDR, of course. Before SDR, you have to know that it was like very difficult to get an equipment, and very, each equipment was very expensive. But now, even with like a very cheap equipment like this one, like the RTL SDR, you are able to do some signal acquisition, and you can then process the signal and then decode it, demodulate it, decode it, etc. So you can do pretty much everything you want. But if you want also to do some transmission things, you have also to spend more money on another SDR that will be able to transmit signal over the air. So everything, depending on what you want to do, you can choose an SDR that can fit your expectations. And here are the example of targets. So we have been focusing during our research. So here are some LoRa devices, like one gateway, one GPS tracker, one do sensor, and one dev kit. But today we mostly look at this setup, because we don't have like a lot of time. So it will be mainly based on one dev kit, one RTL SDR, and a gateway, which is here. So, but first, before doing all the things, we have like some point we have to demodulate the signal. So to avoid doing our own demodulation and also spend a lot of time, there are already some implementation which are the IPP0, BASTI research, but there are also other other modules that allows also to decode the LoRa, but here are the most relevant for our purpose. But the problem is that LoRa also can have like different frequency, different spreading factor and bandwidth. So at some point, if you use one block for each frequency and spreading factor and bandwidth, you will introduce a lot of latency. So you have to do some optimizations. And to do that, you can, for example, recenter all the frequency to one specific frequency. Then you also play with this decimation in order to to feed the blocks with the minimum sample rate, and like that you can work with pretty much all, for example, European frequency, LoRaWAN frequency, and like that you can demodulate what you want in uplink and also in downlink. And here is our tool. So our tool is able, for example, to use to parse, to generate, and also to brute force, to decrypt, to capture also packets as pickup, and also many features. It is also developed in Python, so it's very flexible, and you can also develop your own feature based on what you want. Also, to be clear, there's already some implementation that is available for free, which is the parsing and generation feature that you can also see in the contribution of Scapy, which is the tool to parse and generate some protocol stacks, for example. So actually, you can actually use Scapy and the contribution layer, which is LoRaWAN. So let's do a little demo of our tool. So actually, it looks like follow. I will show you this window now. So now let's go to this window, and I will show you how it will be done. So first, also, we'll also show you how to use the RTL SDR with that. So here's the RTL SDR. We'll plug in the RTL SDR first, like that, and then let's go back to this window. We will just run the flow graph and see what happens. We can see an FFT and also waterfall here. And after that, we have to go to our project. So in our project, we have something called LoRaWAN code here. So we can, for example, I will just copy the line. So like that, I can be very fast and just say that I want to output a pickup like that. So let's now just try to decode what will go inside this, after the capture. And then let's go back to this view. So now let's just plug in our dev kit like that and see what happens. So after a certain time, normally you should see a packet normally here. And also you can see, for example, a downlink here and an uplink because I have already programmed a downlink packet in the network server in order to respond to the first uplink. So you can see, for example, a counter of 0 here and then a counter of 1, and everything gets decoded like that. It's pretty easy. Now let's go. Let's continue. You can also see in the waterfall that we are actually capturing the signal from different frequency, which is clearly good. So you can also do a maxwell like that and see what is happening. Let's go to the interactive mode, and with the interactive mode, we can, for example, see what is happening. So let's, for example, just retrieve the first packet of LoRa like that was capturing the pickup like that, so we can already see the same packet as before. And then we'll use also a function that is associated to the version 1.0 and decrypt, brute force the key that is associated to the MIC. And by doing some testing, we can find a key that is appropriate for that, and then we will use that key to decrypt the packets. And so you can see with decrypt FM payload that we get the clear text payload, which is good. So let's go back to the slides now and continue. We can also inject frames if we want, for example, using a specified dongle, and using that dongle, we can then reproduce a replay attack, for example, in APB mode, in order to, for example, if you capture a packet after the counter has been sent to the maximum after a certain time, you can reuse a packet and then try to DOS, for example, an end device. So actually, this is one of the vulnerability you can, for example, replay with the same scenario. Now let's talk about an important part, which is the fuzzing protocol stack. And it can be interesting because some implementation use open source stacks. So for example, LoRaWAN stack, there's also basic station for the gateways. So actually, Also, what is interesting is that very few vulnerability have been sent, also have been published on that stack. So it can be also interesting to find some other vulnerability. So that's what we also try to do. But first, we had, for example, for flooding LoRa mic node stack, as it is source code, we could, for example, use AFL++ in order to automatize some flooding tests and in order to get, to get some vulnerability, maybe try to find some bugs and then try to confirm them as vulnerability. But first, we had also to remove all the architecture-specific code in order to make it work, because actually it's using some architecture-specific codes at some points, some function that are specific to some architecture like STM32, etc. So as we wanted to make it run on x86, we had to, for example, use to retrieve the important function, which is the process ready Rx down, which is like the function that will be, called once it gets a receive packet. And then we also remove some specific function in order to make it work, but still by not removing the logic as well. And like that, we also we have developed our own architecture in order to get, for example, from LoRaPWN some generated packet. For example, we can generate packet, or we can also capture packet, and then we can minimize them. We can then, after that, try to instrument some binaries in order to do some mutations. And then based on the inputs, we can, for example, get some crashes and then classify the crashes and then try to see if we face some vulnerability or not based on the crashes. Here is an example of a running token giving us crashes, and then when we use the classifier, we get a crash report which looks like that, which tells us also about the backtrace of the crash, so we can also get some idea of the crash if it's exploitable or not. For closed-source binaries, it's much more difficult. For example, for the regular packet forwarder, we have exactly the same function which is used for parsing, but it's a very small part, and all the logic which is in the upper layer is not available in open source. So at some points, we had to emulate this code, and to do that we can use Unicorn Engine or Killing, because actually it is closed source. But the problem with Dragino firmware is that it's only available in MIPS MSB architecture, which is broken for Killing or Unicorn Engine from now. We can still do some over-the-air fuzzing, but still it's not very good to scale. But there are also some alternatives. You're using, for example, debugger to instrument the binary. For the exploitation, we can expect that, for example, after triggering a bug, we can have some denial of services. We can also, for example, for successful exploit, we can leak some keys. We can also do some arbitrary code execution, backdooring, etc. But it's kind of challenging because at some points, you don't know the version, you don't know how it is compiled, you don't know also the instruction set at the beginning, you don't know, the targets, and you can, and based also on the architecture, you can have also some limitations. So, it's so kind of challenging. So for the conclusion, as you may see, SDR is a nice approach to go very low level. You have more flexibility, and then you can also manage everything in Python. But still there are there's a lot of optimization to be done also, because we have made some optimization, but we could also use GPU to run some blocks, some part of the blocks, in order to have a better, less latency that we have, for example, using CPU, for example. Hunting for stack protocol vulnerability is interesting, as you may see, because it's like a vector that wasn't exploited before, and is not as exploited as we see. Mainly cryptographic side was exploited, but we can see that it can have a great impact depending on the context. And also there's a lot of improvement to be made on the emulation. So thank you very much, guys. It's finished for me, but if you have any question, please ask. And also, I'm freely available on Twitter and LinkedIn, so if you have also any question, I'm also easy to find. Thank you very much and see you later. Bye.